Welcome to the HEOR Insights YouTube channel. In this explainer, we will cover the core concepts of network meta-analysis, which is a critical statistical technique in health economics and outcomes research. We'll structure this session into 5 key parts. We'll start with foundational definitions, and then we'll move all the way through to practical application.
So let's begin by defining network meta-analysis and establishing why it's so important in HEOR.
A network meta-analysis, which you'll also hear called an MTC, or mixed treatment comparison, expands on standard meta-analysis. Instead of just comparing one treatment to another, it allows us to analyze an entire network of interventions at the same time, giving us a comprehensive view of their relative effects.
The primary reason we use NMA is for health technology assessment, or HTA submissions. You see, most clinical trials might compare a new drug to a placebo, but HTA bodies need to know how that new drug stacks up against all the other relevant treatments on the market. NMA is the statistical tool that bridges this exact evidence gap.
NMA really serves 3 critical functions. First, for decision-making, it helps payers rank treatments based on their effectiveness and safety. Second, for evidence synthesis, it lets us maximize the use of all available data by connecting different trials. And third, for cost-effectiveness, it generates the relative risk inputs that are essential for building economic models.
Now, to really understand how an NMA works, we need to break down the different types of evidence it uses. You can think of this as the geometry of the evidence network.
First, we have direct evidence. This is the most straightforward type. It comes from head-to-head clinical trials where, for example, drug A was directly compared to drug B within the same study. This is considered the highest quality of evidence for that specific comparison.
Next is indirect evidence. This is what allows us to compare treatments that have never actually been studied together in one trial. For instance, if drug A was tested against a placebo in one study, and drug B was tested against that same placebo in another study, we can use the placebo as a common anchor to mathematically estimate how drug A compares to drug B.
And finally, we have mixed evidence. This is where the real power of NMA comes in. When we have both a direct trial of A versus B and indirect evidence of A versus B through a common comparator, the NMA combines both sources. This integration gives us a more precise and robust estimate of the treatment effect.
Conducting a network meta-analysis isn't just a simple calculation. It follows a very rigorous, multi-step process that's governed by established research practices, like those from ISPO. This workflow begins with a comprehensive, systematic literature review to identify every relevant trial. After that, a critical feasibility assessment is done to make sure the trials are similar enough to be combined. Then, a network plot is built to visualize the evidence connections. And finally, the data is synthesized using advanced statistical methods, with Bayesian approaches being very common in HEOR.
The validity of any NMA really depends on a few key assumptions. It's absolutely essential to understand these assumptions to be able to correctly interpret the results.
HTA bodies will scrutinize these 3 assumptions very closely. The first is similarity, or transitivity. This means the trials in the network have to be comparable in terms of their patient characteristics and study designs. Second is homogeneity, which means the results within any single direct comparison are consistent. And third is consistency, which requires that the direct evidence and the indirect evidence for the same comparison are not in conflict with each other.
So, what do the outputs look like? A primary one is the league table. This grid presents the relative effect for every treatment compared against every other treatment. You'll see an effect measure and a credible interval. A result is statistically significant if that interval does not cross 1.0.
Another key output is the rankogram. This chart displays the probability of each treatment being the best, the second best, the third best, and so on for a specific outcome. It gives us a probabilistic view of where each treatment sits in the hierarchy.
The Sucre score summarizes that rankogram into a single percentage. A score of 100% means a treatment is certain to be the best, while 0% means it's certain to be the worst. It's a useful summary, but it is a simplification, and it should never be the only thing you use for decision-making.
Okay, let's put all these concepts together and walk through a common scenario to see how NMA is actually used in practice.
Here's the situation. You need to show how your drug X compares to a key competitor, drug Y, to get reimbursement. The problem, no trial has ever compared them directly, but both have been trialed against an older drug, warfarin. This is a classic case where an NMA is necessary.
Using warfarin as the common comparator, the NMA produces this result. The hazard ratio is 0.95, and you can see the credible interval runs from 0.80 to 1.15. Because that interval crosses 1.0, we conclude there's no statistically significant difference in efficacy. This finding immediately shifts your value strategy towards things like cost minimization or demonstrating a better safety profile.
So, to summarize the difference, a standard pairwise meta-analysis is limited to one comparison, using only direct evidence. A network meta-analysis, on the other hand, evaluates an entire network of treatments using both direct and indirect evidence. Its comprehensive outputs make it the essential tool for answering comparative effectiveness questions for HTA and pricing. This leads to a crucial final point. An NMA will always give you a precise answer, but you have to ask, is it the right one? The key takeaway is that the conclusions from an NMA are only as valid as its underlying assumptions. You must always critically evaluate whether the trials in the network were truly similar enough to be combined before you can trust the results.